we have spent this series designing the software around the model: context, memory, tools, verification, policy, and orchestration. I'm Mehrdad, and this video begins the frontier section by changing who controls that software. Let code own the loop, then invoke the model only where the work requires judgment. For many agent workflows, the harness should be an ordinary program, not a clever prompt pretending to be one. Looping, branching, sequencing, and deciding when to stop are deterministic jobs that conventional software already handles reliably. Yet, many agent designs assign those jobs to the model alongside the reasoning work it genuinely performs well. The model must choose what runs next, whether to call a tool, and when the process is complete. That mixes probabilistic judgment with deterministic execution. When control flow becomes flaky, the problem is often architectural, not a weakness we can prompt away. The core claim has two parts, beginning with direct ownership of the control flow. Write the loop, branches, retries, and approval points yourself instead of inheriting a framework's hidden execution path. Then decide deliberately who orchestrates each part of the workflow. In many production tasks, deterministic code should drive the procedure and call the model only for reasoning or generation. The important question is not which framework looks most capable. Ask whether the program or model should own execution, state, and termination. This diagram shows the design fork by placing two possible orchestrators side by side. On the left, the model chooses each step, calls a tool, reads the result, and decides whether to continue. Control flow lives inside an accumulating conversation, so flexibility comes with drift and uncertain termination. On the right, code owns the loop, branches, order, state, retries, and stopping rules. The model still performs the intelligent work, but it does so inside a bounded call. The model can be identical in both designs. Reliability changes because the program now holds the loop. 3 recurring failures reveal why this choice matters, and none begins as a prompt writing problem. First, token usage grows because the complete history re-enters context on every model-directed turn. Second, control flow hallucination appears when the model skips a required step or invents one outside the procedure. Third, completion becomes unreliable when the model stops early, continues indefinitely, or misunderstands the stopping condition. These failures are architectural whenever probabilistic reasoning must also perform deterministic bookkeeping. Moving that bookkeeping into code makes behavior testable, bounded, and observable. There is a related design choice in the action space we give the model. A JSON tool call selects one predefined function with arguments shaped by its schema. Composing several tools may require repeated model round trips, even when ordinary code could express the sequence directly. CodeAct instead lets the model emit an executable block that can loop, branch, combine tools, and inspect execution feedback. Errors become information the model can use to revise the action. JSON remains useful for constrained interfaces, while code offers a richer space for composition and self-correction. Code ownership also changes the shape of context, connecting directly to our earlier context management discussion. A model-driven loop usually maintains one transcript, and every turn appends more history to that same growing sequence. When the program owns control, each model invocation becomes a node in a call tree or directed acyclic graph. The harness gives each node only its arguments, relevant evidence, and the results it actually depends on. Context depth now follows call depth, not the length of the entire run. Token explosion is no longer inevitable because the architecture does not require one universal transcript. Once code owns the loop, multi-agent orchestration becomes easier to reason about through familiar software concepts. A subagent becomes a function call, while an orchestrator worker, pipeline, or hierarchy becomes the program's call graph. A handoff passes arguments into that function and returns a value containing evidence, status, and errors. A failed agent is therefore a failed call that code can catch, retry, substitute, or route around. Coordination remains difficult, but ordinary error handling exposes failure instead of hoping another prompt will recover. Code as orchestrator is not a universal answer, because some tasks have no procedure we can specify beforehand. Reach for code when steps are known, repeatable, and subject to auditability, hard limits, or reliable termination. Long-running workflows benefit especially because token growth, retry policy, and stopping behavior must remain under explicit control. Use a model-driven loop for exploration, rapid prototyping, and open-ended tasks where discovering the structure is part of the work. The engineering skill is choosing deliberately for each system section, rather than defaulting to one orchestrator everywhere. Place reliability in code and judgment in the model, then define that boundary intentionally. This follows the principle established at the series beginning. The model supplies intelligence while the harness supplies dependability. Here, the harness is literally a program whose behavior we can inspect, test, interrupt, and change. When the loop is ours, reliability no longer depends on the model remembering how the runtime should behave. Carry these 3 takeaways forward. First, own the loop by writing deterministic control flow directly and choosing who orchestrates each part. Second, executable code provides a composable action space, while code-owned control turns an endless transcript into a call tree. Third, agents become functions over a graph, so failures use ordinary retries, substitutions, and fallbacks. Keep the model-driven loop for genuinely open-ended work where the procedure remains unknown. That is the code-driven harness. Let the program own execution and call the model where judgment creates value. If this series helps you, subscribe to Multi-Agent Academy and connect with me on LinkedIn. Next is video 19, Self-Evolving Harnesses, where the agent rewrites its own code and validates whether each change improves the system. I'll see you there.